Hi, and welcome back to the Implementing and Administering Cisco Solutions, the CCNA 200-301 video series course by EC Council. My name is Glenn Singh. In this video, we are going to discuss Cisco wireless architectures and various access point modes. So let's dive on in. A Cisco access point can operate in one of two modes. Well, a couple of other modes, but most commonly, in terms of the Cisco wireless architecture, there's an autonomous mode an access point can operate in. This means that each access point is actually assigned with a management IP address, which simply allows the network administrator or the network engineer to remotely manage this device. Each access point is independently managed. As more access points are added or inserted onto the network, the data VLANs will need to be spanned across all switches on the wired network using trunk links between switches. In this diagram, we can see we have multiple autonomous APs, and these are our autonomous APs down here. Each of these APs are independently managed, because each of those have their own unique management IP address. So this means if we have, let's say, a network administrator, and let's call this guy here Bob. If Bob wants to manage AP1, Bob will need to independently or manually manage this particular access point, whether it is to create a new SSID or network name or change the password. But what if Bob has to make this change across all devices within the organization? Well, that means Bob also needs to log into this AP, then this one here, and even this one. The thing about it is with using an autonomous AP is really good if you have a very small network. If you have a large network with, let's say, multiple access points like 10, 15, 20, 25, and even more, it becomes a bit more challenging because many times a network administrator or a network engineer will need to ensure the configurations are the same throughout all wireless access points within the entire network. So using an autonomous deployment is good if you have a small network. As your network grows, you will require a very special device called a wireless LAN controller. Also, notice that each of these APs may have multiple SSIDs, and each SSID, as a service set identifier, can be associated with a different VLAN. So for example, we have 3 VLANs, VLAN 40, 60, and 80. So most likely, we probably have, let's say, at least perhaps 2 wireless networks, or let's say 3. So each of these VLANs can be associated with each of our wireless networks. So therefore, let's say we have a wireless network called CCNA1. CCNA1 may be associated to VLAN 40. So therefore, anyone connects to the CCNA1 wireless network, they will automatically be assigned to VLAN 40 by default. Furthermore, your wireless LAN controller can be a cloud-based device. So in a cloud-based architecture, the wireless LAN controller is simply deployed in the cloud. This model allows each access point to receive a management IP address similarly to the autonomous architecture. A simple example of a cloud-based architecture or a cloud-based deployment is a Cisco Meraki solution. The Cisco Meraki cloud model simply allows a wireless LAN controller to gather network and Wi-Fi statistics. It is able to also detect rogue devices and radio frequency interference, together with generating reports much more easily. The cool thing about having the controller in the cloud is all you need is a web browser to simply access the controller's dashboard or the interface. As long as there's an internet connection, the lightweight access points will be able to connect and exchange information with the controller in the cloud. In addition, the cloud-based architecture or the cloud-based deployment provides a single dashboard to simply allow you to configure all of your APs simultaneously. So let's look at this deployment. So let's imagine we have a wireless LAN controller in the cloud as shown here. Now, even though that there are physical wires that are connecting our APs, such as let's say AP1, AP2, AP3, and AP4, as long as these APs, as in a lightweight access point, as long as these APs are associated with a controller in the cloud, a management link is used to connect each AP to the actual controller in the cloud. So this means, let's say we have Bob once more. If Bob wants to make a change on a network, let's say Bob wants to create a new network name. Let's say the new network name is CCNA 2. Well, Bob can simply log on to the wireless LAN controller in the cloud, make the new adjustment. Once Bob saves the adjustment, the wireless LAN controller will then push the configurations to each of these APs simultaneously. So therefore, Bob work is very simple to accomplish. When it comes down to Cisco wireless architectures, there's one known as split MAC. With split MAC, both a local wireless LAN controller and a lightweight access point is implemented. So this means the controller is definitely deployed on-prem or on-premise. Once a connection between a lightweight access point and a local or in-house deployment of the WLC is done, a special tunnel is established between these two devices. The name of the tunnel is called the Control and Provisioning of Wireless Access Point. This is short, or in short, it's called a CAPOAP tunnel. The CAPOAP tunnel simply allows the controller, which is of course installed within your company, to actually exchange data and manage the lightweight access points. Furthermore, the CAPOAP tunnel allows each access point and the wireless LAN controller to be separated both geographically and logically. So this means to say, all you need is one wireless LAN controller within your company, and you could be able to control or associate access points that are at remote branches to your single wireless LAN controller. With split MAC, this allows different VLAN traffic to deliver or to be delivered to a specific AP without the need of creating any trunk ports on your switches. The wireless LAN controller is responsible for handling the radio frequency management, client authentication, security management, quality of service, and association and roaming management of each lightweight access point. So therefore, this load or this responsibility is all handled by the wireless LAN controller. So the lightweight access point simply manages the radio frequency transmission, the MAC address or the media access control management, and the actual data encryption between the wireless network and the wireless client. In this diagram, we can see even though we have a physical link between the controller on the switch and the switch on the lightweight access point, we have a CAPOAP tunnel that is deployed between the WLC and the lightweight access point. The CAPOAP tunnel operates on two ports. For CAPOAP control, it operates on UDP port 5246, while the CAPOAP data tunnel uses UDP 5247. Access points operate in different modes. So Cisco access points are designed to operate in either autonomous mode, which is independently managed, or in lightweight mode. In lightweight mode, they are centrally managed by a wireless LAN controller. However, these modes can be further broken down. So let's look at local. With local, this is a default mode for a lightweight access point, which allows the access point to provide one or more basic service set or BSS using a specific channel. When the access point is not transmitting, it will scan other wireless channels to determine the level of noise, interference, and even detect any sort of nearby rogue access points. Rogue access points are simply access points that trying to trick the users to connect to them simply to steal data and gather confidential information. Another mode is called monitor mode. In this mode, the access point does not transmit any data at all. However, it is able to receive incoming transmissions. This mode allows the access point to function as a dedicated sensor for checking, let's say, intrusion detection system events such as rogue access points, and determining the position of stations, or let's say the position of clients using location-based services. Another mode is known as Flex Connect. In Flex Connect, an access point can switch traffic between SSIDs, switch traffic between an SSID and a VLAN if the CAPO tunnel to the wireless LAN controller is down. However, it can only do this if the access point is configured to do so. Another mode is known as Sniffer mode, or just Sniffer. In this mode, the access point dedicates its radios simply to capture any IEEE 802.11 traffic from any nearby sources. Once the traffic is captured, it forwards it to a computer running a protocol analyzer software such as Wireshark for offline packet analysis. Cisco access points can operate in rogue detector mode. In this mode, the access point is configured to operate by detecting rogue devices simply by correlating MAC addresses found on a wired Ethernet network, or defined by IEEE 802.3 network, with those MAC addresses that are found on an IEEE 802.11 wireless network. Another mode is called bridge mode. In bridge mode, an access point can be configured to operate as a bridge between two networks. Two access points in bridge mode can be used to link two locations that are separated by some sort of geographic distance. Two additional modes are called FlexBridge and SC Connect. With FlexBridge, this mode simply allows the access points to operate in a mesh-like infrastructure. So therefore, each access point is connected to every other access point within the actual network. With SC Connect, this allows the access point to dedicate its radios to enable spectrum analysis on all wireless channels. The data is sent to a computer running a spectrum analyzer software, such as, let's say, MetaGeek Channelizer, or even Cisco Spectrum Expert, to simply discover the sources of any sort of wireless interference. In this video, we took a look at exploring Cisco wireless network architectures, and you have learned about various Cisco access point operating modes. In the next video, we'll take a look at understanding the physical infrastructure connections of wireless LAN components. I hope this video has been informative for you, and I hope to see you in the next one.